So my wife comes home the other day and she's got some bald head moisturizer that she found for me at the store. And she said, "Oh, I thought you would really enjoy this." And I said, "What, is there something you're trying to tell me?" And she said, "Well, yeah, I noticed a couple of little ashy patches there that you might need to take care of." Ashy patches, band name, I called it. And I said, "No, is there something else that you're trying to tell me?" And she said, "Well, no, that was it." And I said, "I'm going bald?" Hey everybody, welcome to PS 231. So at the end of the previous lecture, I talked a little bit about what game theory is. And you're like, "Oh no, you talked way too much about what game theory is." Your point's well taken, but that's my job, is to keep you inspired. And part of what I talked about was the role that contemplative and competent decision makers play in game theory. And I was specifically trying to avoid a particular word, which is a loaded word, rationality.
We're not gonna take this!
That's what we're going to talk about today. So we're going to try to put some mathematical bones underneath the flesh of what I meant by contemplative and competent decision making. Rational choice theory doesn't have to be mathematical. It doesn't have to be game theoretic. Rationality springs up in all sorts of different parts of the social sciences and the decision sciences more generally, depending on how you want to define things. And a lot of this is trying to figure out what consistent choices look like. And by consistent, I mean consistent enough that we could model them mathematically using functions. And you're like, "Oh God, I hope the C block from last lecture was behind us." Oh no, it'll never get behind us. And really, that's the goal. When I say rationality, I don't mean selfish. I don't mean sociopathic. I don't mean I'm just trying to do what's best for me. That's not what I mean by rationality. There are flavors of rationality, informal flavors of rationality, where terms like that pop up. And if we're being honest, most people's informal conception about what people mean by rationality involves selfishness, potentially nastiness, stuff like that. But that is not what I'm talking about today, nor throughout the rest of the class. More often than not, we'll make modeling choices where the people that we're trying to figure out what they do, we'll model them as if they're rational sociopaths, but that doesn't mean that we had to. That isn't baked into our enterprise. Those are modeling choices rather than features of the models that we're talking about. That sounds like hair splitting that apparently I can't afford to do, but it's actually really important because it means that what you should be focusing on today isn't like the substantive aspects of the story. It's actually a more limited enterprise than that. My goal today is just to show you 3 different ways to see the same thing, and by that same thing, I mean consistent choices made by contemplative, competent decision makers, rational decision makers. And you're like, "Why would you show me 3 different versions of the same thing?" Well, part of it is I want you to get 3 different angles. I mean, if you can see something from all sorts of different angles, then you have a richer idea about what it is. But just as importantly, I have no particular way of knowing which version of rationality is going to be the first one to resonate with you. And I don't mean resonate in terms of, "Oh my God, now I know how to go behave." I mean in terms of figuring out exactly what we're doing, the aha moment. The earlier that you get an aha moment in one of the 3 flavors, the easier it will be for you to understand the other 2 flavors, because my job as a teacher today isn't just to show you the 3 flavors, but to show you when they all taste the same. Oh God, that's an extended metaphor that should have died early. I want to show you when the 3 different things I'll be showing you all tell you roughly the same story. So pay attention to the linkages between things and not just the things themselves. So go get yourself some caffeine and strap in, and we'll get to it. In the A block, we'll give you the most traditional version of rational choice theory in the form of binary preference relations. Binary preference relations aren't what we'll work with the most in the class, but it's the easiest way for me to convey the rationality postulates to you. We'll put mathematical bones underneath the flesh of contemplative and competent. I'll give you 2 formal criteria that have to be satisfied for the sort of people that live in the worlds we'll be developing for the next 13 weeks of the class. The main idea undergirding binary preference relations, as you may have guessed from the name, is that it's about binary comparisons. If I give you one alternative, say Coke, and another alternative, say Pepsi, how do you compare those 2 things? Now that's really annoying because it means that if I've got a bunch of different alternatives, then I have to be thinking about every potential pair of them. And that's part of the implausibility of the contemplativeness axiom. And you'll see what we mean once we have a picture up of what's going on. So in the B block, we'll try to make things a little bit easier by using the most traditional way to model rationality in the form of utility functions. So we'll be talking about how a decision maker might be able to take alternatives like Coke and Pepsi and turn them into happiness numbers. That's a stupid story, right? There is no happiness number part of your brain, but we'll be able to proceed as if that's how people make decisions, so long as they satisfy certain criteria that will have been given to you in the A block. Now, the problem with these two models, the binary preference relation version of rationality and the utility function version of rationality, is that neither of them is verifiable. I can't tell you if somebody lives up to binary preference relation rationality, nor to utility function rationality, because those are things that I can't see. I'm not a neurologist. I don't know what's going on in your brain. So in the C block, we'll talk about what you can learn from observed choices in the form of revealed preference theory. The idea there is, if I give you a bunch of alternatives and I see you choose one, or say that you could potentially imagine choosing some subset of them, then that means that you are revealing something about how you feel about them. So I observe your choices, I can see them, and the question is, under what conditions do those observed choices provide enough data to say that somebody is being contemplative and competent? So the goal is to say, when is the A block like the B block? When is the A block like the C block? And therefore, when is the B block like the C block? That sounds confusing, but that's actually a really important part of what we do when we try to find patterns in things, is say that things are the same. If you can't say that two things are the same, then you have no hope of identifying a pattern between them. So we've got a big tree and the trunk is rationality, and we've got three beautiful branches to look at. So let's get climbing. Let's get started. So here in the A block, we'll talk about the most traditional way of stating what rationality looks like in the form of binary preference relations. You're going to crush every dinner party you ever go to if you just say, you know what I want to talk about today? Binary preference relations. People will think that you are so dazzling. They'll be so amazed by your sparkling wit and personality. None of this is true. Do not try this at dinner parties. I speak from experience. No, I don't. I've never been to a dinner party. So in the intro, I told you that the underlying idea of binary preference relations is that it's about comparing pairs of alternatives. So throughout today's lecture, we're going to need some set of alternatives. We're going to have a finite set of alternatives. So you can enrich the theory if you wanted to look at richer sets of alternatives, like not finite ones. For example, when you want to set a preferred tax rate, you could choose any tax rate you wanted to between 0 and 100%. And we won't be able to model something like that today because we'll be looking at a finite number of alternatives. But that's just to keep our lives easy. I just want to be able to show you things from the cleanest vantage possible. If you have questions about what infinity would look like in the context of rational choice, just let me know in class. So we're going to have this finite set of alternatives X, and for the purposes of today's lecture, we're going to have a particular set of alternatives, okay? And I've arrayed them so beautifully, right? So you have 4 choices in today's lecture: Coke, Pepsi, Dr. Pepper, and Sprite. And apparently the Encyclopedia of Landscape Design. No, we're not choosing landscape design books. We're just choosing among pops. And it's pop, not soda, you cretin. And the idea of binary preference relations is that you don't just look at all 4 bottles of pop and say, I'm going to choose one. The idea of binary preference relations is that we care about how you feel about 2 of them in comparison. So just for example, if I show you a Coke and a Pepsi, I'm going to ask you how you feel about these 2 things. In particular, I want to know if you like one more than the other, or if you're indifferent between the 2. So if I show you a Coke and a Pepsi, you can think about how you feel about them. If I show you 2 political parties, you can think about how you feel about them, even while you're voting from a large ballot with all sorts of alternatives. However, there are many choices in life that are genuinely binary, like a yay vote and a nay vote, or go to war and don't go to war. So sometimes binary is enough, but sometimes binary isn't enough. The idea of binary preference relations, however, is that we're going to take complicated decision problems and turn them into a bunch of binary comparisons. Now, this is insufficient. I need to know not just how we feel about Coke versus Pepsi, but also Coke versus Dr. Pepper, Coke versus Sprite, and also Pepsi versus Dr. Pepper, and also Pepsi versus Sprite, and finally Dr. Pepper versus Sprite. So the idea is that we take 4 things And we're going to think about how we feel about every pair of them. And I'm going to introduce a notion of liking something at least as much as something else, okay? So I'm going to have the set of alternatives X, and on X, I'm going to define something called a binary relation, which is just something that tells you about a relationship between any pair of the alternatives. You already have some familiarity with binary relations, you just haven't done it on sets of alternatives necessarily. But if I say to you that 4 is greater than or equal to 3, that's a statement, and it's a true statement. And what's in the middle there, right? So you've got the 4 and you've got the 3, but what's in the middle is this relation is greater than or equal to. And actually a big part of our goal is figuring out when we can treat alternatives and the relation is at least as good as, the same way that we look at numbers with the relation greater than or equal to. And that'll be exactly what we do in the B block, but let's get our rudiments down first. So I'll introduce this squiggly greater than or equal to sign, which is read is at least as good as. So I take every pair of alternatives and I have this potentially is at least as good as symbol. So if I write Coke is at least as good as Pepsi, or X is at least as good as Y, that's just a statement, all right? And we're gonna take that as given. We have a decision maker and they have a bunch of feelings, and our question is how we model their feelings. And I don't mean all their feelings. This isn't like Inside Out. I mean their feelings about the alternatives. Now, this squiggly greater than or equal to sign is great, but actually I think it's easiest for us to think about this more visually. So let's just imagine that the set of alternatives is a blob with some dots in it. So I've got the set of alternatives X, and it's got Coke, Pepsi, Dr. Pepper, and Sprite in it. Okay, just 1, 2, 3, 4. I'm sure that wasn't the right order. I just feel like an 8-bit bad guy right now. Coke, Pepsi, Dr. Pepper, Sprite. We'll see how long I can keep that up. If I want to say that Coke is at least as good as Pepsi, I could write that as a statement, but I could equivalently just draw a little arrow that goes from Coke to Pepsi. One-sided arrow. That arrow means that Coke is at least as good as Pepsi. I'm allowed to have two-sided arrows as well. I won't use two sides because that'll make it harder for you to keep track of them, but I can have an arrow that goes back from Pepsi to Coke. So right now, I've got two statements to talk about. Coke is at least as good as Pepsi, and Pepsi is at least as good as Coke. So that's gonna be my notation for this throughout today's lecture, and on your problem set. And you're like, I just did a problem set. Yeah, you gotta do 15 of them. You think you get this charm and beauty for free? No, you gotta do 15 problem sets. Now, I should also note that I'm allowed to have an alternative be at least as good as itself, right? So I could put a squiggly arrow on the Sprite. So here I'm saying Sprite is at least as good as Sprite. So I've got Coke is at least as good as Pepsi, Pepsi is at least as good as Coke, Sprite's at least as good as Sprite. And the question is gonna be what properties have to emerge in a picture like this one for us to say that somebody is contemplative and competent. Before we get to that though, I want to define two other notions of preference that are descendants of our notion of weak preference is at least as good as. I'm going to define these next two relations in the terms of at least as good as, which we're going to treat as axiomatic. And a lot of this is about figuring out what are the right axioms for our study. Today is the day of axioms. So in particular, I'll write that X is strictly better than Y. Alternative X is strictly better than alternative Y, if and only if X is at least as good as Y, and Y is not at least as good as X. So in the context of the picture, let's just say I've got a dot that goes from Coke to Dr. Pepper. So if I don't have an arrow that comes back from Dr. Pepper to Coke, then that means that Coke is strictly better than Dr. Pepper, right? A one-way arrow with no reciprocal arrow means strict preference, is strictly better than. That's the same as is strictly more than, and that's why the symbol for it is this squiggly greater than sign, strictly greater than sign. You're like, oh, it's all coming together. Oh, don't worry, I'll ruin the rest. So that's strict preference. That's just a descendant of weak preference, right? I just defined what strict preference is in terms of weak preference. I can also define indifference in terms of weak preference. So I'll write that X is indifferent to Y, alternative X is indifferent to alternative Y, if and only if X is at least as good as Y, and Y is at least as good as X. So in particular, let's say that I've got an arrow that goes from Pepsi to Sprite, and back from Sprite to Pepsi, so that Pepsi is at least as good as Sprite, and Sprite is at least as good as Pepsi. Now I've got both of them, right? I've got both of them, which means that Pepsi is indifferent to Sprite. It also means that Sprite is indifferent to Pepsi. I could write that just the same way. You can convince yourself of that in a doodle if you want to. So now we've got our notion of weak preference, that's our axiom, and we've just defined two other relations, strict preference and indifference in terms of that. And it's with all that equipment in mind that we're able to define what we mean by a regular preference relation, which is going to be our first notion of rationality. And there are going to be two assumptions, two axioms that we're going to impose on our decision maker in terms of what their doodle among all these alternatives has to look like. The first of those assumptions is called completeness. Completeness. Completeness is going to be what I mean by contemplative. So when I say that a weak binary preference relation is complete, what I mean is, for all pairs of alternatives, call them X and Y. X is at least as good as Y, or Y is at least as good as X, or both. Remember, our default setting for or is or both. So completeness means that X is at least as good as Y, or Y is at least as good as X. So let's go to a fresh doodle. Let's get a fresh doodle. We've got Coke, Pepsi, Dr. Pepper, and Sprite. Fresh doodle. Also a reasonable band name. Completeness carries a little hidden thing in there, because I didn't say for any distinct alternatives. I said for all pairs of alternatives. And I'm allowed to take the same alternative out of that set twice, right? We said before that a set can have multiple versions of the same. That means I have to have every alternative against itself. So to begin with, I need it to be the case that for every alternative, that alternative is at least as good as itself. So in other words, Coke has to be at least as good as Coke, Pepsi has to be at least as good as Pepsi, Dr. Pepper has to be at least as good as Dr. Pepper, and Sprite has to be at least as good as Sprite. That's what these squiggly arrows mean. Notice that if I don't have all four of them, then I'm already off to a bad start. So if I get rid of the Sprite one, now we haven't satisfied the condition already. So let me put that back so that I can sleep at night. This property is called reflexiveness. Sometimes you see it as a separate axiom, but it turns out that reflexiveness is covered by completeness. So for starters, we don't have anybody rational unless they have the ability to say that every alternative is at least as good as itself. Now, that seems to not be based on rationality. It doesn't seem to be based on the alternatives. That seems to be a matter of making sure that the words that we're using make sense. If I ask you if you're as tall as yourself, the answer is yes, you're as tall as yourself, right? That's because I said at least as tall as. That's not that I didn't say are you strictly taller than yourself, which you're not. You're the same height as yourself. That's just a bit of a consistency check just to make sure that the language that we're using makes sense. And if we lived in a world where reflexiveness didn't happen, that's part of completeness, then we'd have a very difficult theory to think our way through, because that would mean that if I said to you, hey, is Coke at least as good as Coke? And somebody would say, no, Coke is better than Coke. So that's the first half. But with completeness, I said every pair of alternatives, not just every alternative against itself, which means that I'm not allowed to have any holes. I can't have any two-way holes, and that includes the diagonal, right? I can't have any holes. So in order for me to come up with a complete preference relation, it's not enough for me to have all the squigglies. I also need to make sure I've got at least one arrow, could be two, that's the or both, between every pair of alternatives. So let's say I'm going to close this up for now by saying that Coke is strictly better than Pepsi, Coke is strictly better than Dr. Pepper, Coke is strictly better than Sprite, Dr. Pepper is strictly better than Sprite, Pepsi is strictly better than Dr. Pepper, and that Pepsi and Sprite are indifferent. So we've got Coke beats Pepsi, Coke beats Dr. Pepper, Coke beats Sprite, Chewy says hi. Dr. Pepper beats Sprite, Pepsi beats Dr. Pepper, and we've got indifference down here. Notice that I now have no holes. I've covered both diagonals and I've covered the entire outside. So for completeness, we need squigglies on everything. Apparently I'm doing a jump rope. And we need no gaps. No gaps are allowed. So that's completeness. That's what I mean by contemplative. Okay, that means that somebody has thought hard enough about the set of alternatives that they can't look at two alternatives and say, I don't know. You're allowed to be indifferent. If you're indifferent between Pepsi and Sprite, that's not the same thing as not knowing how you feel about Pepsi and Sprite, right? So when you're voting, probably for most federal offices that you go vote for, you have a clear picture about how you feel about the alternatives. But then if you go down that ballot and you find yourself down at the bottom of the ballot for some office you've never heard of, you're like, oh, I didn't realize that we needed a manager of the Parks Department of Pawnee, Indiana. You're like, I didn't know we had to vote for that person. And you've never heard of the parties that the alternatives are from, and you've never heard of the people, and you have no idea what the job is. Completeness doesn't make a whole lot of sense there. You don't have the information, you don't have the wherewithal to have thought that through. So completeness, it's a little bit of an annoying assumption. The reflexiveness part isn't annoying, but Having thought through every pair of alternatives to the point that you know them well enough to be able to say you're at least indifferent between every pair of alternatives, that's a lot of thinking that somebody has to do. And we'll see that actually that can be avoided a little bit if we think hard about choice. That'll be in the C block, preview of coming attractions. If I offer you 2 words out of Jabberwocky, 2 nouns out of Jabberwocky, then you can't reasonably compare them. You might be a nice person and say, hey, I'll say I'm indifferent just so that you can say that I'm a rational person. But chances are excellent that you're not indifferent. You're actually apathetic. You don't care. You don't know. You don't know how you feel. Now, part of this is making sure that we as modelers have chosen X appropriately. We need to choose the right set of alternatives so it's plausible that our decision maker could think through every pair if they needed to. Now, with 4 bottles of pop, I'm pretty sure that I know how you feel about these things. You might hate all carbonated beverages so that you're indifferent between all of them. You hate them all. Or you might have a strict preference ranking where you go, look, I like colas best, so I go Coke, indifferent to Pepsi, strictly better than Dr. Pepper, strictly better than Sprite. Right? You might know exactly how you feel based on your own preferences about pop. But if I ask you how you feel about 2 alternatives and you don't even know what the words mean, this is hopeless from the start. So I got to choose X right. I'm the modeler. I'm the analyst. I have to choose X appropriately. We're modelers together. We got to choose the right X. So that's what I mean by contemplative. You've thought hard enough that you know how you would compare every pair of alternatives if somebody asked you. The second axiom of regular preference relations is going to be about competence, and that's going to be transitivity. This is the transitivity assumption. And when I say rationality, what I really mean is transitivity. Completeness is there mostly to make our lives easy. It's to make sure that the mathematical devices that we're going to use enough information that we can work with them without too much trouble. You could come up with a theory of rationality that was just reflexive and transitive, but that's a nightmare and it's not fun for me to work with, much less fun for you to work with. But transitivity is the main rationality postulate, and every version of rationality that you see includes something like transitivity. This is going to be the primary straw stirring the drink, so that when I say to you rational, what I really mean is transitive. I don't mean selfish, I don't mean mean, I don't mean sociopathic, I mean consistent, I mean competent. So here's the assumption. Suppose that we've got some trio of alternatives, call them X, Y, and Z. It could be Coke, Pepsi, Sprite. And suppose that we see that our decision maker has the following pattern. They have X is at least as good as Y, and Y is at least as good as Z. So I might like Coke at least as well as Pepsi, and Pepsi at least as well as Sprite. So I've got a little chain. I've got a little chain going. And that means I should be able to learn something. So here's an if. If it is true that you like X at least as much as Y and Y at least as much as Z, then it's also true, then you also get to learn that X is at least as good as Z. So if I said to you that Coke was at least as good as Pepsi and Pepsi was at least as good as Sprite, don't you think that you should be able to reasonably infer that I like Coke at least as much as Sprite? Yeah, probably so. That means that there isn't like some cycle going on. You'll see a picture of a cycle here in just a second. Cycles are the primary instantiation of what we might consider non-rational behavior. Non-rational behavior in the context of a binary preference relation. We don't want to see cycles pop up. These cycles are nightmarish for us from a numeric standpoint for reasons you'll see in the B block. So let's go back to our example. Now, there are all sorts of chains in this picture that I've drawn. This doodle has a lot of chains. So for example, notice that I like Coke at least as much as Pepsi and Pepsi at least as much as Dr. Pepper. Then it must also be true that I like Coke at least as much as Dr. Pepper. And notice that it is. We're good. We're good on that one. It has to be every time. I said for any triple of alternatives XYZ. So passing one test isn't enough, but that's at least one test that we passed. It's a for all. So notice also that I like Coke at least as much as Dr. Pepper and Dr. Pepper at least as much as Sprite. So it needs to be the case that I like Coke at least as much as Sprite, and I do. I like Coke at least as much as Pepsi and Pepsi at least as much as Sprite. So I need to like Coke at least as much as Sprite, and I do. I like Coke at least as much as Sprite and Sprite at least as much as Pepsi. So that means that I have to like Coke at least as much as Pepsi, and I do. I like Pepsi at least as much as Dr. Pepper and Dr. Pepper at least as much as Sprite. So I have to like Pepsi at least as much as Sprite, and I do. This is what I mean by competent, is consistent. I've passed a lot of tests so far. I have consistent choices to the point that you could reasonably expect something if you knew that 2 things about me were true. That's the whole point. However, I fail a test. Notice that I like Sprite at least as much as Pepsi and Pepsi at least as much as Dr. Pepper. Which means I have to like Sprite at least as much as Dr. Pepper, and I don't. So I just violated transitivity because I've got a cycle. And that chain goes from Sprite to Pepsi to Dr. Pepper to 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 Sprite to Pepsi to Dr. Pepper. We want gravity to go one way. We can't have a cycle like this. Now I could solve this little problem two ways. And you're like, why would you solve the problem? Actually, it's kind of interesting. If you show somebody the fact that they've got some cycle in their preferences that they violate transitivity, a lot of the time they'll go, oh yeah, good thinking. I'm sorry that I missed that. And you won't tell them that it was bad. You'll just be like, oh, you weren't very consistent there. And they're like, you're right. There's something normatively appealing about making consistent choices, even if we don't always live up to that, right? I could fix that one of two ways. I could make Sprite indifferent to Dr. Pepper by having Sprite at least as good as Dr. Pepper as well, right? So a two-way arrow. Or I could get rid of the Sprite to Pepsi arrow, right? That would sort of snuff the cycle out before it started. So we say that a binary preference relation is regular if it's complete and transitive. These are our two primary rationality postulates. And that's what we mean by rationality when we're telling this version of the story. Contemplative enough that they can compare every pair of alternatives, completeness, and competent enough that they make consistent enough choices that we can draw reasonable inferences, transitivity. And it turns out that there are some perverse ramifications of the completeness and transitivity of the weak preference relation that we'll be talking about in the problem set. You're like, oh, joy of joys. And those interesting wrinkles are just things that we have to accept because they're things that come from the axioms. This is the primary axiom. It can be reasonable in terms of weak preferences, but no matter what, it's got some downstream consequences that force us to be humble in our interpretations of what comes thereafter. There are scope limitations. We can only study certain kinds of decision makers that live up to these two postulates. Now you might be wondering, why would we go through this entire thing? And it turns out that these two postulates are going to be really important for being able to facilitate our version of the study. In the B block, we'll talk about the simplest version of the story of utility functions. See you there. So here in the B block, I want to tell the version of the story that you've probably heard before if you're a political science major, the utility function version of the story. So observe that it's really annoying to have to walk around with a binary preference relation for a large set of alternatives, right? So we were looking at 4 alternatives, and it turns out that with 4 alternatives, there's all sorts of data that you would have to know about the existence or non-existence of a weak preference relation. So you could like Coke more than Pepsi or not, Pepsi more than Coke or not, Coke versus Coke or not, Pepsi versus Pepsi or not, right? So just there alone, there's all sorts of different arrows that could be drawn or not drawn. There's a lot of data that you need for 2 alternatives. And as we add more alternatives, we're adding more and more comparisons that we have to know or not know about. That data set that we would have to know for binary preference relations would get very large very quickly. The doodle would become so complicated that we wouldn't be able to make any sense of it. So it's interesting to wonder whether or not we could summarize the information in a given doodle with something that told us everything we needed to know with far less data. We don't want to have to know every single binary comparison if we don't have to. Now, the story that we told was plausible enough about contemplative and competent, but it would be nice if we didn't have to work that hard. It would be nice if we didn't go into every single model that we wrote down with 10 gajillion comparisons that we had to make. And it turns out that the main tool that people use to simplify binary preference relations is something called a utility function. In the 1800s, it was viewed that utility actually existed, that you have some part of your brain that taps into this utility thing so that there really are happiness numbers. And as best as anybody can tell, that was a bit of a misguided idea. However, utility is still a useful fiction for us to tell, even if there isn't a utility function part of the brain. You know, I think a lot of it was just people felt very optimistic about what science can do and the ability to measure everything. And it turns out some things aren't measurable. And utility is one of those things that isn't measurable, but that doesn't mean it can't be useful. We just have to introduce some conditions under which it works. So here's what I'm going to do. I'm going to begin with a finite set of alternatives. Call it X. And if you need to motivate things, say that X equals Coke, Pepsi, Dr. Pepper, and Sprite. And you're like, this all seems so trivial. You could call them 4 political parties if you wanted to. I mean, the labels don't really matter. We're talking about the relationships between things, not the things themselves. I'm assuming that you're thinking about something interesting. And I think that pop is very interesting. So we've got a Coke, a Pepsi, a Sprite, and a Dr. Pepper. And the idea is I want to assign every one of these things a number. I want to come up with a utility function, U, that reads in alternatives and spits out happiness numbers. So it's a function with a domain of the set of alternatives and a codomain of the real numbers. And what that means is I've got U of X. For any alternative, I get U of X, and that's just a number. So that means that I've just got a blob with some dots in it that reads Coke, Pepsi, Sprite, Dr. Pepper. And I've got another blob with dots in it that's real numbers, or just the whole real line. Okay, so I've got a function that reads in alternatives and spits out happiness numbers. That isn't true. That isn't true. That doesn't mean it can't be useful. And the idea is not that it's going to be like, oh, I like Coke way more than Pepsi, so Coke gets 1,000,000 happiness points and Pepsi gets 1. The idea is that we need this just to tell us enough about the ranking. We want the highest ranked alternatives to get the highest happiness numbers, and the lowest ranked alternatives to get the lowest happiness numbers, so that if you saw that one happiness number was more than another happiness number, you could rightfully infer that the first alternative was at least as good as the second. Okay? This is about how do we convert squiggly greater than or equal to regular greater than or equal to. So for example, let me just recreate the doodle that we ended up with at the end of the A block, where I liked Coke at least as much as Pepsi, Coke at least as much as Dr. Pepper, Coke at least as much as Sprite. See, I don't want to say this every single time. Pepsi at least as much as Dr. Pepper, Pepsi at least as much as Sprite, Dr. Pepper at least as much as Sprite, Coke at least as much as Coke, Pepsi at least as much as Pepsi, Dr. Pepper at least as much as Dr. Pepper, and Sprite at least as much as Sprite. Think about all the things I just had to say. I don't want to have to do that. I want to make this easy on myself because I'm lazy. So here's what I'm going to do. I'm going to give Coke the highest number because I like Coke strictly more than Pepsi, Coke strictly more than Dr. Pepper, and Coke strictly more than Sprite. So I'm going to give it a 4. I'm just going to give it a 4. I'm going to send it to 4. Why not 5? It could have been 5. I'm just choosing easy numbers to work with because I'm lazy. I like Pepsi less than Coke, so I can't assign it a number strictly higher than 4. I like it strictly worse, so I should give it a number strictly less. Right? But I like it strictly more than Dr. Pepper and Sprite. I like Pepsi the second best, so I'm going to give it a 3. This isn't that hard, right? This was hard. This is easy. I like Dr. Pepper the third best. It's strictly worse than Pepsi and Coke, but it's strictly better than Sprite, so I'm going to give it a 2. And Sprite's the worst. I'm going to give it a 1. Clearly, I like Sprite the least because it doesn't have any caffeine in it. How else am I going to power my way through these things? So now I've come up with a set of numbers that summarize all of this chaos. This is ugly. This is simple, right? And it turns out it conveys all the same information. I like Coke strictly more than Pepsi, and I have 4 strictly ahead of 3. I like Coke at least as much as Coke, and I've got 4 is greater than or equal to 4. In fact, 4 is equal to 4, right? I've got all of the ranking information that was contained in this binary preference relation. All of that ranking information is conveyed in this set of numbers. And notice that I've got a lot more data that I have to think about here than I have here. Here, I just need one number for every alternative. Here, I've got a quagmire of arrows and non-arrows. And just to repeat, this isn't true. There is no part of your brain, as best as I can tell, that's the utility number part of your brain. I've been thinking about it. I've been ruminating on the subject. Sometimes I just turn off all of the beautiful lights in the studio, and I just go like this. And I never find it. I never find it because it isn't there. You don't realize it, but that performance that you just saw was my version of incredibly deep meditation. And I didn't find it. I didn't find the utility function part of my brain. I found out all sorts of other things about myself. I hadn't realized just how much I love Ella Fitzgerald. I just learned that about myself, but I didn't learn where my utility function part of my brain is because I don't have one. Oh, let's not forget Dizzy Gillespie. Oh, look at those cheeks. Look at those cheeks. I'm not good at pointing it from the monitor just yet. Oh, look at those cheeks. If you don't know who Dizzy Gillespie and Ella Fitzgerald are, oh God, please remedy that. Turn off this movie right now and go and look for movies of them. They're way better than this. And you're like, oh yeah, that wasn't real hard to figure out. Shut up. Now here's an interesting question. Suppose that I had a cycle, a strict preference cycle in my set of alternatives. Suppose I had a cycle. Would I be able to do this? So let's just go over to another doodle. Let's just say I had Coke, Pepsi, and Sprite. All right? Let's make it complete. So Coke is at least as good as Coke, Pepsi is at least as good as Pepsi, Sprite's at least as good as Sprite. And let's make it complete by closing in every arrow. And here in particular, let's say that Coke is strictly better than Pepsi, Pepsi is strictly better than Sprite, and Sprite is strictly better than Coke. So I've got a cycle. It goes from Coke to Pepsi to Sprite, and so on. So that's in there. Now, let's say I wanted to try to assign numbers. So I like Coke strictly more than Pepsi. So just to get things started, I'll say, just to get things started, that Coke gets a 3 and Pepsi gets a 2. And I like Pepsi strictly more than I like Sprite. So let's say that, so I need to give Sprite a number that's strictly less than 2. So we'll give it a 1. But then I like Sprite strictly more than Coke, but I've got a 1 on Sprite already and I've got a 3 on Coke already, which means that the numbers don't convey the same information. It turns out that the relationship between the number thing and the preference thing depends on completeness and transitivity. So before I get into that relationship all the way, let me just give a formal criterion for when a preference relation is well behaved enough that we can use a utility function to summarize its information. So suppose that we've got a set of alternatives X, a finite set of alternatives X. We say that a binary preference relation on X is representable if there exists some utility function, call it U, that reads in alternatives and spits out happiness numbers, such that alternative X is at least as good as alternative Y, if and only if the utility of alternative X is at least as high as the utility of alternative Y. Notice that what that means is I want to be able to take squiggly greater than or equal to on the alternatives and reliably convert them to happiness numbers, U of X and U of Y. Notice also that I want to be able to go the other way if I need to, so that if I see something about the happiness numbers, I can reliably infer something about the preferences. So what representability means is that there's a two-way relationship, a completely clean relationship between the alternatives and their rankings as encoded via binary preference relation, squiggly, and the numbers as encoded through the utility function. So representable means that you're clean enough here that you can go here if you need to, and vice versa. The relationships are what matter. It's the relationships. It's not just the things, it's the relationships between the things. And here's your first theorem. You ready for a theorem? I'm not going to prove it, but here's the theorem. Theorem, a thing that is always true. Here is a statement that is unambiguously true. And you're like, oh, I'm going to brace for impact. It's probably pretty predictable. So suppose we have a set of alternatives X that is finite. A binary preference relation on X is representable via utility function if and only if it's complete and transitive. What does that mean? It means that completeness and transitivity are fully equivalent to clean enough to be able to summarize information through utility functions. Right? That's what that means. That's the if and only if part. So I'm saying I see somebody out in the wild and they tell me all of their binary comparisons, and in so doing, they tell me that something that's complete and transitive. They appear to be a contemplative, competent decision maker per the axioms that we laid out in the A block. And what I'm saying is, if I see that person that is contemplative and competent, I can model them with the utility function. And also, if I see somebody out there that just randomly assigning happiness numbers, apparently they just walk around like this. 4, 3, 2, 1, this is what they're doing. Look at that blur. Check out the 24 frames per second cinematic blur. Oh, you're loving it right now. You are getting your money's worth. It all just boils back down to 8-bit bad guys. And if I see somebody out there that just pointing at things and giving them numbers, which is a huge if, there's nobody that does that. But if I saw that person, I would be able to say, oh, well, there's a binary preference relation in there somewhere that's complete and transitive. I can go either direction. Notice that I don't need it to be a unique utility function. right? So let's go back to our previous example where I gave 4, 3, 2, 1 to Coke, Pepsi, Dr. Pepper, and Sprite, respectively. Okay? I didn't have to give them 4, 3, 2, 1. I could have given them 5, 3, 2, 1, a million, 2, 3, 2, negative a million. The numbers don't matter. It's the rankings that matter. All that I care about is that the rankings encoded with the numbers are the same things as the rankings encoded with the arrows. And the idea is that our decision maker is going to be inclined to choose the things that are high in their preference relation ranking and therefore high in their utility function ranking. In particular, highest and highest. Now, there's no reason to say that it has to be a unique highest thing, right? So if I was indifferent between Coke and Pepsi, then I'd give them both a 3 maybe. And I would probably choose one or the other if you forced me to pick one. But I would be indifferent. I would just say, oh, give me a cola. But that's the basic idea of utility functions, is when we maximize a utility function, when we choose the alternative that gives you the highest utility, which is probably an uncharitable interpretation of rationality that you've heard before. What that means is that alternative that got chosen is in like the top set of alternatives. It's something there that's either strictly better than everything else, or it's indifferent to things that are in the top and then strictly better than everything else. And that's a well-formed enterprise. That's a well-specified enterprise, so long as we have a decision maker who is contemplative and competent, which is to say has a binary preference relation that is complete and transitive. Sometimes that's appropriate, sometimes it isn't. But every time you see a utility function in a paper that you read in other class, that's tantamount to saying, look, I've got a bunch of arrows, and I don't want to talk about the arrows because there's too many arrows. So instead, I'm going to talk about numbers, which are easy. And you're like, numbers aren't that easy. You'll see that they're a bit of a reprieve. Now, utility functions, we're going to extend them in weeks 3 and 4. So please put a pin in this, because it turns out that seeing things this utility function way, the act of assigning higher numbers to things that you like more, that's going to be a really important part about how decision makers navigate uncertainty. And we'll see that there's all sorts of interesting wrinkles that emerge there. But we have a little bit more business before we can conclude. I want to talk about choice, which I just sort of glossed over, and it's something that's worth taking seriously. So in the C block, we'll talk about what we really mean by rational choice theory. See you there. So here in the C block, we're going to take the thought of rational choice very seriously by talking about something called choice mappings. And you're like, oh boy, this sounds really exciting. This is hard. I just want to preface this with this is going to be the hardest block of today and one of the hardest blocks. And you're like, would you just stop with the hard stuff and move on to the easy stuff? Once we get to the easy stuff, you're going to be able to stop and enjoy all the views. This is one of those things where I can't wait to show you some cool stuff as the class goes. And if you ask me, this is cool stuff already. But I know that this kind of feels like leg day for a lot of you nascent weightlifters. And the thing is, if you want to go on a long hike and enjoy beautiful vistas at the top of mountains, you need to work on your cardiovascular and your legs. This is all hypothetical. I'm not going anywhere. I'm not going to leave this house ever again. This is where Chewy and I are going to hunker down. So the theory of choice mappings was developed mostly within economics because there's a lot more observable choices out there. But it's a nice way for us to think about what verifiability means for these two fictions that we've told up to this point. Binary preference relations. Somebody could tell you, oh, I like Coke at least as much as Pepsi, but there's no guarantee. One, they might not know their preferences all the way. Not everybody knows their preferences really well, right? Or two, they could just lie to you. People lie all the time if you haven't noticed. And there's no reason that if I'm running an experiment and I'm like, hey, do you like Coke at least as much as Pepsi? Pepsi at least as much as Coke, or both? Well, if it was something more controversial than how you feel about the cola wars, then they might lie to you. So they might not know, or they might be lying to you, or both, or neither. There just doesn't have to be a clean relationship between people's announced preference relations and their actual preferences. If those exist, which there's no guarantee that they do. And certainly we know that utility functions don't. So we need to think about what it would look like to be able to make verifiable choices. If I'm running an experiment, what would I be able to do from choices that I can observe? What could I learn from that? And under what conditions does the thing that I learn consistent enough that I could use a utility function if I wanted to? So this theory of revealed preference is venerable in the study of microeconomics, slightly less important in political science, but I think really important for a lecture like today's. So sorry to put you through it. So here's the idea. This is a two-part story. So we have a set of alternatives like before, and let me just, I messed up the tray, but let's say I've got a set of alternatives on a landscape book: Coke, Pepsi, Sprite, and Dr. Pepper. So that's my set of alternatives X. And here's the idea. I'm going to take a bunch of subsets of that. Now, what's a subset of that? Well, every individual bottle of pop is a subset. Sprite, as a set, is a subset of Coke, Pepsi, Sprite, Dr. Pepper. So too is Pepsi, Coke, and Dr. Pepper. So that's every one way, every singleton subset of my set of alternatives. Sprite and Pepsi is a subset of Coke, Pepsi, Sprite, Dr. Pepper. So too is Sprite, Dr. Pepper. You're like, oh, I need you for this. I could have a three-way subset as well, right? So I could have a Dr. Pepper, a Coke, and a Sprite. That's a subset. That's a three-element subset. Finally, I might have a subset with all four alternatives. Boy, the book is just dying because it's just not very expeditious, and I don't have that much memory card. These files are big, by the way. If you're curious about the movie making, just let me know. I don't know if it's interesting to you, but like the raw footage for one of these lectures is like 250 gigabytes. That's why I have to talk so fast. And you're like, yeah, talk faster, fat man. Shut up. So I'm going to have a collection of subsets of X. Okay, collection of subsets of X. I'm going to call that my set of menus. So I've got a set of menus where every menu is some set of somethings from the set of alternatives. It might be one alternative. We're not going to talk about that because, hey, how do you choose between Sprite and Sprite? You better take the Sprite. So we're going to be looking at multiple element subsets for the most part. I mean, I guess technically speaking, it isn't a problem to think about the singles, but let's not go there. So my set of menus is some collection of subsets. It might be all of the subsets, but it might be only some of the subsets. Maybe I'm not that well funded. Maybe my funding agency was stingy, and they're like, I'm not going to give you enough funding for you to look at every single subset of your set of alternatives. Notice that if I've got a finite set, the number of subsets in it is 2 to the number of elements. So if I've got 4 alternatives, there are 16 subsets. If I've got 100 alternatives, like at a mini mart, then that's 2 to the 100. That's a massive number. No funding agency is generous enough to let me do that, and I don't have time to think about every comparison. So the idea is that we're going to present our decision maker with a bunch of menus. We're going to give them a bunch of menus. If we're feeling ambitious, we might give them every menu, but that might not be feasible. Okay, so I've got a set of menus. We're taking that as exogenous. Those are the givens in the model. The primitives of the model so far are a set of alternatives and a set of menus of those alternatives. There might be all of them. There might be strictly less than that. It depends on the context. It depends on what we, the analyst, are able to do. Now here's the story. In this story, the decision maker will be presented with a menu, and every time they get a menu, they have to give you a non-empty subset of the menu. So if I offer a Pepsi and a Sprite, it's my subset. So if I offer you Pepsi and Sprite, you have to choose a non-empty subset of this. So for example, you could choose Pepsi and that's it. You could choose Sprite and that's it. And in so doing, you're essentially revealing that you like Pepsi strictly more than Sprite or Sprite strictly more than Pepsi. Or you could essentially reveal that you're indifferent by saying, I could imagine choosing one or the other. One day I choose one day I choose the other. I mean, do you have the same lunch every day? Do you have the same dinner every day? No. Does that mean you're irrational on the days that you don't have your very favorite food? No. That just means that variety is the spice of life. You could imagine choosing Chipotle over Potbelly. You could imagine choosing Potbelly over Chipotle. Now, if I give you 3 alternatives, right? So a Sprite, a Pepsi, and a Coke. You could imagine choosing one. You might just choose the Coke. You might choose a pair of them. You might choose just the colas. You're like, well, I'm not much of a Sprite person because I like caffeine. So I can imagine choosing Coke. I can imagine choosing Pepsi, in which case C of that menu would be Coke Pepsi. Or you could say, you know what, I don't care. Just I could imagine choosing any of the three. So the idea is that C of a menu, so if I have a menu, call it M, then C of M can't be the empty set, and it has to be a subset of M. So that's what the choice mapping does. It's not a function because it can spit out multiple dots, right? This is something more general. You might call it a mapping or a correspondence. We're not going to be using these things very often. I'm just trying to get your bearings on this. And the idea is that I've got a bunch of menus and I'm going to observe all of these choice mappings. Okay? So what C does is it reads in menus and it spits out potential choices. Now this is fully observable. If I go to the mini mart and there's somebody in the mini mart and they're staring, dazzled by all of the different pops available at the mini mart. Okay, they're dazzled. They're just completely dazzled. Just think about the miracle that is a mini mart sometime, much less the miracle that is a drugstore. Think about the most mundane drugstore on the corner of the most mundane streets you could think of. And think about how miraculous that store would seem to somebody from the 1800s. Right? And I could go up to somebody and they're staring there and they're over here and I go to them, oh, by the way, I need a complete preference relation. So please tell me how you feel about Monster Energy drink versus Nesquik. And they're like, I was here for a beer. I'm like, I need a complete preference relation, please. But I can't observe their choices. I could creepily stand outside the mini mart. And then when they leave with whatever they chose, I'm like, oh, I am taking note of that. Or if I'm an experimentalist, I could be in a laboratory and present people with a set of alternatives and see whom they vote for or which pop they choose. This is observable. That's what's nice about it, is it's observable. It's verifiable because choices can be seen. Preference relations and utility functions can't be seen. So the question is, what's a reasonable consistency requirement in this world? In this world where there's feasible menus and choices being made from that menu. What is consistency there? What does contemplative and competent look like there? In particular, what does competent look like there? What would be something akin to transitivity in this world? You can pause the video about that if you need to. Try and guess. What would a condition about consistency look like in this world of menus and choices? We had consistent preferences before. We had consistent utilities before. What are consistent choices? Welcome back to the two of you that went and got a Monster Energy drink. I'm assuming none of you got a Nesquik. Although, sometimes Nesquik is pretty awesome, right? You go on a road trip, you get you a soft batch cookie and a Nesquik, and life is good for the first 5 minutes. And then after that, it's just a nightmare. There are all sorts of consistency checks in this world, okay? And if you're interested, come ask me sometime about some of the other ones, but I'm going to give you the most traditional consistency requirement, which is called the weak axiom of revealed preference. So here's the idea. This is a little bit tricky, but if you pause at every step that you need to, you'll be just fine. That's just good advice in life. So here's the idea. We say that a choice mapping over some set of menus from some set of alternatives satisfies the weak axiom of revealed preference, or just warp. We say it satisfies warp if, and there's going to be an if then, right? So when I said consistency, that means if you know that one thing is true, then you also have to get to know that something else is true. It's just that the things that you learn, the thing that you know, and the thing that you would like to know, they're going to be more complicated in this world. But it's the same structure. It's the same structure. X is at least as good as Y. Y is at least as good as Z must imply X is at least as good as Z. It's going to be the same sort of idea here. So here's the idea. If there exists a menu, call it M, with two alternatives, call them X and Y on it. Right? So I give you a menu that has Coke and Pepsi on it. And Coke, X, is one of the things chosen. So if I've got some menu where X and Y are elements of that menu, and X is an element of the things chosen from that menu. So that's my if. That's my if. So you just learned three things. There's a menu. On that menu are two alternatives, call them X and Y. And X is one of the things chosen off of that menu. It could be X and something else was chosen, but all I know is that X is one of the things chosen off of menu M. Then something can't be the case. We're going to rule something out. We're going to rule something out. We're going to say it can't be the case. It cannot be the case that there exists some other menu, call it M prime, with X and Y on it. Y is chosen off of M prime and X isn't. So in other words, if I reveal to you that X is at least as good as Y by choosing X off of a menu that includes Y on it, then if you give me some other set of alternatives that has X and Y on it, you can't reveal Y to be strictly better than X. But here you said, I'll choose Y and not X, which means that Y is essentially strictly better than X. And over here you told me that X was at least as good as Y. Those seem incompatible, right? Those seem incompatible. And the idea of the weak axiom of revealed preference is you have to make consistent enough choices that as you reveal preferences in one choice context, we ought to be able to reliably know some things will be true in another choice context. So just to give you an example from our balls of pop. Suppose that I had the menu Coke, Pepsi, and Sprite. And suppose that on that menu, Coke, Pepsi, Sprite, I chose Pepsi and Sprite. And suppose that I had another menu, Coke, Pepsi, Sprite, Dr. Pepper. And suppose off of that menu, I chose Coke and Dr. Pepper. Do you see the violation? There's two violations in that case. Because in choice context 1, on the first menu, Coke, Pepsi, and Sprite were available, and you chose Pepsi and Sprite. Or you said, I could imagine choosing Pepsi or Sprite. Like you don't get both of them. You're essentially saying, I could imagine choosing one or the other, but I would not choose Coke. You can rule Coke out. Then you gave me another menu with just more things on it. Coke, Pepsi, Sprite, and Dr. Pepper. And then you say, well, in that context, I can imagine choosing Coke or Dr. Pepper. You're like, well, what's so great about Coke when Dr. Pepper is on the menu that wasn't great when Dr. Pepper wasn't on the menu? That doesn't make any sense. It doesn't make any sense. If you called that to somebody's attention, they'd be like, yeah, that doesn't make any sense. And if there's somebody who likes to make sense, which is an if, but if there's somebody that likes to make sense, they'll correct their views on this. And if they're not, then they won't, and that's fine. I don't care. It just means I can model one of them and not the other. So that's the weak axiom of revealed preference. Okay? That's my consistency check in choice menus, in rational choice. So here's a result that's going to have it's going to be a rather weak result because I'm going to impose some strong assumptions. We want to make weak assumptions. I haven't said this. It's nice if you can make weak assumptions that seem to hold in a lot of different contexts. You want to make weak assumptions so that you know that something is true a lot of the time, but sometimes you have to introduce strong assumptions just to make things conveyable to undergraduates. So I'm going to tell you something that's true. I can show you stronger things if I wanted to, but I really don't want to get too far into it. But here's the result. Suppose that I've got some finite set of alternatives X and a set of menus over X that includes every two-way and every three-way comparison. So I might not have every menu, but I at least have every two-way menu and every three-way menu. So I've got every XY and every XYZ. I don't have to have every WXYZ, right? So I've reduced this is still a cheap study. This is a cheap study, so long as I don't have too many alternatives. This is a feasible study. So here's what I can do. So I can essentially come up with a binary preference relation using a choice function. So I can say X is revealed to be at least as good as Y if there exists a menu where X and Y are both on it and X is one of the things chosen. So I can turn choices into preferences, and I can turn preferences into choices by saying, if I knew that X was at least as good as Y in a binary preference relation, then for any menu that have X and Y on it, it can't be the case that Y is chosen and X isn't. That's essentially what I was just talking about in terms of warp. I'm just trying to say I can go from choice mappings to binary preference relations and vice versa, and that way I can tell you something that's true about their relationship. So here's the true thing about the relationship. Suppose I've got a set of menus that has every two-way and every three-way comparison. Then, a choice mapping on that set of menus satisfies the weak axiom of revealed preference if and only if the binary preference relation you made from that choice mapping is complete and transitive. So in other words, if you satisfy warp, then I can figure out how you satisfy completeness and transitivity. And if you satisfy complete and transitivity, I can figure out how you satisfy warp, just by making sure that I can move from one world to the other easily enough. Notice that a preference relation is representable if and only if it's complete and transitive. In other words, if I've got a complete and transitive preference relation, I can use it to come up with a utility function and vice versa. And that means that warp satisfying choice mappings also can go to utility functions. I've got all three relationships in my little tripod of rationality. Tripod of rationality, not a band name, but that's like the second EP put out by a band. And I don't know what the name of the band is, but they just turned out Tripod of Rationality. Warp gives you complete and transitive, gives you utility, gives you warp, now it's a virtuous cycle where all of these three things are equivalent. Satisfying warp under appropriate menu limitations is the same as binary preference relations that are complete and transitive, is the same as representable. They're all the same thing. So when I say rationality, I don't mean selfishness. I don't mean meanness. I don't mean spitefulness. I don't mean anything related to self-interest. I just mean consistent enough that I can come up with a utility function. And we just saw two flavors of consistency: completeness and transitivity, and warp satisfaction. So if you have an open mind, we should be able to build some really cool edifices atop this foundation of rationality. And rationality in our class means something relatively limited. If you see it in other classes, it might mean something more. But a charitable interpretation of rationality is no more than this, because this is as much as we need to tell some really cool stories, which I can't wait to do with you. So what did we talk about today? It was a hard one, right? We talked about rational choice, which ostensibly is something that's foundational for game theory. You may have seen game theory before in some of your other classes, or you may have just heard about it. And the idea that gets given a lot of the time is that we talk about rationality and utility maximization and stuff like that. And what gets glossed over is a lot of the really important mechanisms that we're trying to describe when we write down a utility function. There's a lot more to it than just what gets told to you in an introductory capacity. And the idea is that rationality doesn't encode any particular kind of decision-making process. We don't know how people form their preferences. We don't say what their preferences ought to be. We don't say that we know whether or not they like Coke or Pepsi or Dr. Pepper or Sprite. We don't impose anything about that. There's no right way to be rational. There's no set of preferences that are obviously rational and some other set of preferences that are obviously irrational. These are the sort of judgments that we're trying to avoid. The question is, who is consistent enough, contemplative and competent enough, that we can model them? And in particular, that we can model them with utility functions if we want to make our lives easier than binary preference relations and choice mappings. I don't have to think about that every single time. That's really complicated. Utility functions are easy, unrealistic, but easy. The question is, which realistic stories are close enough that we could come up with an easy to use utility function? We don't talk about the processes. We don't talk about the structures of the decision making. We don't talk about who's smart and who isn't. This has nothing to do with that. You could find somebody who likes odd numbers, and if you offered them $1, $3, $5, and $1 million, they would choose 5 over 3, 3 over 1, and 1 over 1,000,000 because 1 is odd and 1,000,000 is even. And that's complete and transitive. That's rational, even if it seems a bit weird to you. So that's what we're talking about here. We're not talking about anything beyond that. Anything that goes past that is going to be part of a given model that we describe. We'll talk about the prisoner's dilemma or the game of chicken or all sorts of different games. And in those games, we'll specify what preferences are. That doesn't mean that we think that they're what the preferences ought to be. They're just a particular story that we're trying to tell using this rationality story. You can interpret today's lecture as 3 different versions of the same story, and where that story is foundational for all of the stories yet to come. I just used the word story a bunch of different times, and you might be thinking, I was told that this was a scientific class with mathematical reasoning and all sorts of different rigorous things that are very scientific. And here this fat man is talking about stories, and stories don't seem like part of the promise. And it's with that in mind that I'd like to refute you with a provocative thought. Let's talk about the fox and the grapes. So once upon a time, there was a fox, okay? And the fox was walking down the road. And as the fox was walking down the road, there was a vineyard along the road. And the fox noticed that somewhere in the vineyard, there was a vine that was higher than all the other vines. And it got unique sunlight. It got more sunlight than all the other vines got because it was the highest. It was the uniquely high vine. And thus, at the top of this vine was the most uniquely beautiful set of grapes that the fox had ever seen. Just imagine the most beautiful bunch of grapes you've ever seen in your entire life, just waiting to be eaten. You can just imagine how, can't you taste them? You can imagine how delicious they are already. And the fox could too. And the fox said, I'm going to get those grapes and I'm going to eat them. So she goes over to the vine, which I just said was uniquely high, and she tries to climb it to go get those beautiful grapes. She's scratching, she's clawing, she's doing everything she can to get up the vine. There's a lot of effort being put into it. But vines are high and vines aren't very easy to climb, and so no matter how hard she works at it, she just can't get a lot of headway going. She never gets close to the grapes. The grapes just remain just tantalizingly out of reach no matter how hard she tries. But they're beautiful, so she keeps trying. She jumps, she climbs, she scratches, she claws. She's going to do everything she can for these grapes. And yet, no matter how hard she works, the grapes elude her grasp. And eventually, after an hour of jumping and scratching and climbing and clawing, the fox says, I just don't know how much more I have in me. She can feel her heart pumping. She can feel her lungs breathing in air at a much higher rate than usual. She can feel the lactic acid pumping through the muscles in her body. She's done. She's spent. She's not going to get the grapes. And eventually, despite her best effort, she realizes that she's not going to get them. We probably could have told that pretty early on, but she wanted to try. And as she resigns herself to the fact that she's not going to eat the most delicious bunch of grapes that she's ever seen in her entire life, she sulks away, disappointed. She mumbles to herself, those grapes were probably sour anyway. That's a beautiful story, right? That's a great story. You've probably heard it, The Fox and the Grapes. If you haven't, you're probably going to remember it. That's an easy story to remember. We talk about sour grapes all the time, right? So sour grapes are part of the vernacular. And whenever we talk about sour grapes, we're referring to the fable of the fox and the grapes as told by Aesop, or somebody that has been collectively called Aesop. And for those of us that have been raised in a particular culture, this is sort of part of the canon, right? So the fables that one learns, that's part of the canon. We tell these stories to children. And these stories convey meaning. The Fox and the Grapes story is a beautiful story in its own right, but as a fable, it also has something else going on underneath it. There's a particular moral that you're supposed to learn. Now you might be wondering, how on earth could I try to learn something from this stupid fable? Foxes don't behave anything like what was just described. Foxes don't walk down roads. Hi, I'm a fox. I'm walking down the road. Foxes don't do that. Foxes don't talk. Foxes don't have linguistic capacities. The fox couldn't walk down the road and see the beautiful bunch of grapes and say, I'm going to get me some grapes. The fox couldn't disappointedly sulk away from the grapes and say, those grapes are probably sour anyway. That's the punchline of the fable, is the sour grapes. The fox never could have said sour grapes, and the reason the fox never could have said sour grapes is that foxes don't talk. So I've got a fox that is implausibly walking down an implausible road and sees implausibly beautiful grapes and implausibly talks about them after the fact, and I'm supposed to learn about what they said. This is an awful story that has nothing to do with how foxes interact with grapes. This story sucks, right? No. The story is awesome. Why is the story awesome, you wonder? Because you're going to remember it. It conveys a really important message to you that you will remember. It lets you know that oftentimes people who work incredibly hard to get something that they want an awful lot and then fail, after the fact they tell themselves they didn't really want it. Now I could say that to you. I could say, well, oftentimes people work very hard to get things, and no matter how hard they work for them, they sometimes fail, and after they fail, they tell themselves they didn't really want it. Or I could plant an image in your mind of a fox jumping and scratching and climbing and clawing and failing. And that image of a fox can't get out of your mind no matter how hard you work at it, right? We've all felt like that fox. We've all jumped and scratched and climbed and clawed and failed. I've had plenty of sour grapes moments, and I'm assuming that you've had some too. And every time you see somebody out in the real world do what we were just talking about, you can say to yourself, boy, that seems like sour grapes. Which is to say that the fable is a device that you use to relate different states of affairs to one another. You can have a sour grapes phenomenon, I can have a sour grapes phenomenon, and they're similar to one another in the sense that they can both be related back to our beautiful device of the fox and the grapes, our memorable, succinct way to make a point, to help you know that two things are similar to one another and they both have sour grapes phenomena. And I'm telling you that when I write down mathematical models about how people behave out in the real world, I'm telling you a fable. I'm trying to give you a succinct, memorable depiction. I'm trying to plant an image in your mind's eye, not of a fox jumping and clawing and scratching and climbing, but rather of somebody making a difficult decision, potentially in a strategically embedded environment. Not because I think that that's how people really behave, but rather because I want to be able to tell you a story. I don't think that foxes eat grapes. I don't think that foxes talk to themselves. I don't think people are irrational. But that doesn't mean I can't tell cool stories, assuming that they are. In other words, this story, no matter how implausible, is still useful to us. Whether or not foxes really talk to themselves or eat grapes has nothing to do with whether or not that image is going to stick in your brain. A story isn't great because it's realistic necessarily. A story can be great because it makes you feel something, or it gives you information. It teaches you something. And when we write down fables in political science, when we write down game theoretic fables, we're just trying to convey meaning to one another. And what this means is that, again, there's a deeply human element to what we're doing, not inside the model. We're trying to study decision makers who are human, but we're also trying to tell stories about them to one another. And it's really hard to tell those stories if we don't simplify the process. I can't write down a short story that covers every single aspect about how foxes make decisions and whether or not they have anything to do with grapes. But I don't need to. In order for me to plant the image of the failing fox in your mind, in order for you to get sour grapes as part of your vernacular, I need to tell you just enough. And I can make assumptions along the way to help you see what I'm talking about more clearly. The same goes for the fables that we talked about today. All three fables told the same story, and that story is the story of consistency, of contemplative, competent decision makers. And what's beautiful is that we're going to be able to take this decision maker that we learned how to model today and accept the fact that she's just as implausible as a fox that wants grapes and talks to herself about it. And even though we're not going to be able to say, oh, well, this person is very realistic, we will be able to say, here's a beautiful book of fables that's based upon this person. And every one of those fables has some meaning to convey. Every one of them has a lesson that I would like to teach you. The book of fables isn't realistic, but that doesn't mean it isn't beautiful. So if you take the next 13 weeks as a book of fables based on today's foundational fable, if you're willing to keep an open mind, if you're willing to be creative, if you're willing to see past the obvious things in front of you, if you're willing to just hold a thought for a second, even if you don't accept it, if you're willing to be a little bit flexible, the next 13 weeks will present a beautiful book of fables for you. Every fable will have a story to teach you. Every one of them will convey meaning. Every one of them, hopefully, will be easy for you to remember and succinct enough that you could tell it to somebody else if you wanted to. That's how ideas propagate. And we need to make sure that they propagate consistently, otherwise we're playing the telephone game with ourselves. So we write them down precisely. I hope you're getting some taste for this mix of the rigorous and the precise and the human and the beautiful. What makes you neither an inventor nor a discoverer, but rather a designer, what makes you an architect, what makes you an engineer, is the ability to take the human and the rigorous and put them together in a way that really makes sense, conveys meaning, and is beautiful. I get worked up about this because I think people want this to be science-y, and I don't know what the hell science is. But what I do know is that one necessary condition of a useful science would be the ability to convey meaning in a precise, unambiguous, clear way, in a way that conveys meaning efficiently. I'm pretty sure that we're working toward that after today's lecture. I hope that you agree. We can talk about it a little bit at this week's meetings if you'd like. But in the meantime, thanks for watching.